So next chapter is another study for the transformer. We try to look into different type of the transformer that may interest you, including the auto transformer, and also how we estimate about the power loss, the impedance, and high-frequency transformer analysis. We're also looking into transformer connection, which we discussed briefly about last week. So firstly, to ask you what's the meaning of auto transformer. This is a really practical name. We have been using transformer for many years. So anybody can give me a hand what's the meaning for auto transformer. Ali, what's auto transformer? Do you mean a transformer is automatic? But you all call it auto transformer.
Primaries can be on the same.
Yeah, secondary and prime winding are the same copper, same winding. We don't separate them. So why we do that? We just make this simple, low cost. In many transformer, if you only want to adjust the voltage, so that means we don't need to have two separate winding. In this case, we can share the same winding. In a way, we can reduce some of the cost, some of the wire. At least we can reduce the copper wire. So that's something we need to do. So for transformer, besides voltage and current conversion, right? What else you can do? Why we need to use transformer? Any other function for transformer? Of course, basic thing we learn will be magnetic isolation, harmonic isolation to differentiate both sides so that you don't have any short circuit due to the earthing, right? And then another thing will be how we're going to connect a number of transformers together. I think I briefly discussed, and so now we go through more detail. So today we go for 5 major sections: how to work with the matching transformer, transformer connection, and auto transformer, three-phase transformer, and transformer losses. Right. So firstly, a matching transformer is really important for power electronics. Even though for audio component, many components, we need to have transformer matching. So typically, for instance, your oscilloscope, then the input will be 1 mega ohm. So that means if you want to have best signal measurement through your oscilloscope, so your probe also need to 1 mega ohm. So that means when you use oscilloscope, you need to be really careful about how to do that. Make sure your probe is 1 meg, and the oscilloscope is 1 meg. If they're not the same, the signal you measure will be distorted. You're not measuring the proper signal. So bear in mind, sometimes your oscilloscope, the input impedance has been adjusted to 50 ohm. Why is that? Because some of the sensor may use 50 ohm. For instance, maybe current sensor. So that is something we need to be careful how to do the matching. I think you all know that in the undergraduate, if the impedances are matched, then we can maximum power transfer. We don't have any standing wave looping in the system. So that's why matching will be important. Another way will be like the audio transformer. For instance, your speaker is 4 ohm, but your system is something like 16 ohm. Then you need to use a transformer to match the speaker so that you got maximum power transfer to the speaker. Otherwise, it doesn't, the audio noise will be there. So that's why we use transformer for the matching. So in here you can see that if we got the turn ratio N1 over 2 is N. So obviously the voltage conversion between them like that, the current conversion ratio between them. So that means if we try to, in the secondary side, we put in an impedance Z in here. So that means the secondary side impedance, of course, E2 over I2. Primary side, we assume the primary side has some impedance, the input impedance, then that means the E1 over I1 here. So putting these two equations together with the turns ratio, then we found that with the relationship between the impedance Z, output impedance, to the input impedance have a ratio N squared. So that means we can use transformer turns ratio N to adjust the impedance we can see from the primary side. So that means if you can see if there's a speaker, we want to change the speaker impedance, then using a transformer, on that side we can see a different impedance for the speaker. Or if there's an oscilloscope, then that is say 50 ohm. I can use transformer to change the 50 ohm sensor into some other impedance, so that in a way you have maximum power transfer. So that's a really typical, a simple way we use transformer. So that means a transformer not only for voltage conversion, but also for impedance matching. So in many ways, when we're looking into the power distribution, somehow we also need to look into that. But of course, for many of the high power distribution, in order to prevent any standing wave in the power system or oscillation, we also need to take care of the impedance matching. If they don't match properly, we may end up with something not the noise harmonic or not maximum power transfer anyway. So that's one of the basic functions we have been using it. So for instance, one of the simple way when we want to calculate some impedance or current. For instance, we got a transformer like this. Primary side, we got 5 ohm inductive impedance. And secondary side, we have 20K capacitive and also 40K resistive. So now the question asks us, calculate primary side current, calculate the secondary side current, calculate voltage across the 40K ohm. So the question is really simple without the transformer. But when we with the transformer, we need to think about firstly, we need to calculate the current in the secondary side. We need to know this voltage. But we also need to know the primary side voltage. But the thing is, we got impedance in here. It's not resistor. We have some impedance in here. We're not quite sure what that impedance is. Because this impedance combined with this together with transformer also share between this impedance and this impedance. So it may be more complicated to use potential divider method to get this voltage, not a simple drop to D. So that's why the simple thing to do will be refer everything to the primary side, become a simple single loop circuit. In this case, we don't need to worry anything about what kind of voltage appear in the transformer side because we can't. We are not that easy to do that. So once we further it to this side, then we can, our impedance can using n square relationship to get to here, become 2 ohm in here, and also 4 ohm in the primary side in here. So once we do that, then that will become a single loop circuitry. Then we can get the total impedance by using the Woodman's RMS, then it's 5 ohm. So input 10 divided by 5 becomes 2 amp. So now we go to primary side is 2 amp. That's the current. And the secondary side, we're just using term rate, so we can get the secondary side current. Once we current, if we flow through resistor, we can therefore get its voltage. So the question before could be complicated to calculate, but once we use transform term ratio, we can therefore get its individual voltage and current much easier than before. We don't need to worry too much about the potential dividing in the presence of a number of the reactive component. That can be quite complicated. So this very simple circuit analysis, I think you did in many years ago in our undergraduate. Very simple, but it's one of the techniques I show you how we're able to understand to use transformer turns ratio to help you the calculation called the impedance matching. All right. I think is it really simple? Yeah. But simple is good. When you try to go through something simple, it gives you a kind of thinking. Yeah. Next will be something we now have been talking about last week. If you got a number of transformers connected in together, like 2 transformers. So in here, if the 2 transformers connect in parallel, primary side and secondary side, then the voltage conversion ratio still equal to the same N2 over N1. But bear in mind that no 2 transformers can be exactly equal or identical. We use identical. So that's why if the 2 transformers are identical, then of course this conversion ratio must be good. But if they're slightly different, then probably we end up with voltage from the V34 and V78 may not be exactly equal. If they're not equal, then there may be some kind of additional losses or maybe circulating current in the secondary side, perhaps in the primary side as well. But theoretically, if they are equal to each other, we are able to do that. So of course, I never recommend you to connect two transformers in parallel in such a way. But that is only for ideal case. If the two transformers are ideal, you're able to do that. Particle transformer, we don't like to do that. But of course, many people still do that. They assume the two transformers exactly equal. But the problem is if they are slightly different in the conversion ratio, maybe different by 1%, 0.1%, then they will end up with some kind of unequal voltage shorting together. That will cause additional losses. Okay. Another connection will be PS. That means the primary side will be parallel. We are now the primary side parallel. If the second side is in series in such a way, then there won't be any circulating problem. Even though the two transformers are not exactly equal, we can still able to connect them in series in the second side, like that. So that means now then the input side is equal voltage. In the second side, we can just use the conversion ratio relationship. Then we can obviously see that the conversion ratio is twice of the term ratio. That's obviously really straightforward. Bear in mind, I mentioned after the dot rotation here, the dot rotation here and here, you're able to enhance the voltage in the second side, double the voltage, right? But however, for instance, if we swap the dot in here, that will cause you the short circuit in the second side. So that's why the dot rotation here will be important to show you how to connect them. All right?
Can you repeat last?
You see the dot rotation here. Let me see if I got any pen. I like to use a pen. Pen, where's the pen? A photo thing. So just say if the more look like positive and negative, right? It's a more positive and negative. Because dot rotation here. So that means we are able to connect these two in series in the second side. Then the voltage, of course, will be double in the second side. So that's what I mean. But however, if the dot rotation here, I have a dot in here, then in a way, then that will become positive and negative. So these two voltage will therefore cancel out. So we got zero voltage at the output side. So in a way, then we can, using this method, to adjust some voltage in the output side. But the disadvantage will be we are using cancellation of voltage. May not be a good way, but in a way, then theoretically we can do that. If these two transformer is not the same turn ratio, when we combine them in such a way, we can have different kind of the output ratio relationship. So that's what I mean. So that means that's one phenomenon when we connect a transformer in PS manner. Primary side parallel and secondary side in series. So another way connection will be SP. Then in a way we can say the primary side we connect in series. Second side we connect in parallel. So of course, when we connect them in parallel, there won't be any voltage issue. But however, we can use this method to refer the secondary side to the primary side. So output will be Vout, but the primary side we are using transformer term ratio. So in this case, we only have half of the conversion ratio because we are now using series connection in the primary side. So simple and straightforward. Yeah. So that means we got many different ways to do that.
secondary side, it is cancelling out, right?
So say again,
On secondary side, we have connected in parallel,
in parallel,
so the voltage is cancelling out.
the voltage between this V34 and V78 are equal. So if this voltage equal, then when they reflect to here, then we got this voltage conversion ratio. Then these two are connected in series to add them together. So happen to be their turn ratio are equal. So that's why we input side will more look like double the voltage.
In previous slide, you mentioned if we are connecting them parallelly, they are cancelling out, right? Zero.
That's right. But now we are not, you see the dot rotation here and here. So we are not cancel anything. We're adding up two primary side together. We're adding. So that's why it more look like the input voltage share equally by this V12 and V56. So that means you can see that now if V in here, we half the voltage convert to the secondary side. So that's why originally single transformer, we got full voltage, but now we only have half voltage. So that means the conversion ratio will be half. So that's another way to do that. So you can see that I showed you a few simple configuration, how we connect the various transformer here. So once you know the basic concept, how we do the connection, you can extend to many various ways, many transformer connect in parallel, series parallel. And then we're going to get things quite interesting. Then another configuration will be, both of them will be in series. Series. So now then, the output voltage. So if I assume these two transformers more look like are equal and share each other, you got half the input voltage, half the voltage conversion ratio here, and then plus the another one in here. So the voltage conversion ratio equal N2 over N1. But in some case, if the V12 and V58 may not share exactly equal, because no transformer can be identical. So I assume that share A portion. This will share the rest of the portion. So in ideal case, A equal to half. But if the A, then you can see putting in here, then add them up together, then still equal N2 over N1. So this equation shows us if these two are share voltage equally, then you use the conversion ratio equal to N2 over N1. In case the two transformer may not share voltage equally, then still using N2 over N1. So that's quite interesting phenomenon. So there's many ways we can connect a transformer, but bear in mind, the dot rotation will be quite important to identify if able to add up voltage or to take out the voltage. And sometimes if they're not sharing equally, you can still able to make them have a simple conversion ratio. So let's look at the other phenomenon, right? Like this one. Now then, if the voltage conversion ratio are not equal, just now we assume them to be equal, but now if they're not equal. So like this one, 1 to 3 or 1 to 2, right? So now the input is parallel. Obviously the input is equal, right? Output voltage, when the V34 are equal to input multiplied by 3. So this one, voltage V78 are equal to twice. Add them together become 5, right? So now then this one will be conversion equal to 5. Very simple, straightforward. You see, when we do this analysis, we do think about how we add the voltage property. Would there be any unequal voltage sorting out the transformer? If sometime we connect transformer improperly, then we may end up with some kind of short circuit. So that's the thing we need to avoid when we're putting transformer together. So we need to have clear mind how to connect them. So now then we have using this dot rotation here. So that means when we adding these two, we just adding these two together. So that's a plus. So now then here we are now reverse the secondary side. The dot rotation is here. we more look like these two voltages are subtract from each other. So that means on the top transformer here, we use 3 times of the input voltage. Bottom side here, because the top rotation reversed it, it's become minus 2V, so the voltage conversion equal 1. So now that this transformer, we can therefore single voltage conversion ratio. So you see, this is quite simple thinking, but the knowledge we get from here will be we are able to use a number of transformer by using different kind of connection, able to build up various voltage conversion ratio. Why is that? Because in some certain limited resources, if we do a transformer, it could be expensive. For instance, if I ask you, I give you these 2 transformers and ask you to produce voltage conversion ratio you 5 and 1, then you can just using a relay, putting somewhere, do this connection, you are able to build up 5 or 1 by using a relay to reconnect it. So that's something electronically, you can still able to change the conversion ratio between 1 and 5. And then for instance, if you have DC to DC power converter, I think DC to DC power converter, you're also using transformer there. Then you can using some kind of the transistor. You can therefore quickly can change from 5 to 1 using 2 transformer connection. Or sometimes you can use the tapping in here, can change the connection. But in here, we don't have tapping. We only have 2 transformer. Then we're able to build up various pattern in the output. So that's the thing I'd like to introduce to you. We can using limited resources, build up a number of voltage conversion ratio. You get that?
So I have a question.
Yes.
So use 2 transformers to transform voltage, the efficiency will be influenced or not?
That's really true. Now, one thing is you can see that now in this one, I think the efficiency of this will be higher than that. Because we are now adding the 2 voltage together, we're not wasting any winding. But in here, we are this 3 time winding and 2 time winding, we cancel out this winding. So probably the efficiency of this one will be lower.
Yeah.
But you can see that sometimes for power electronic design, for double E design, we may not care too much about the efficiency. We care about the cost.
Yeah.
As I mentioned before, in limited resources, you get a new component will be more expensive. But transformer uses 99% efficiency. We raise about 1%, so what? We don't care. But he raised 1 transformer will be much more expensive. So that's why in design point of view, at least we can have using a simple relay or MOSFET, you can able to change from 5 to 1 within 1 nanosecond, right? That's a nice thing to hear that. And then we also have other connection, like in here, the same kind of transformer, and then we swap them. Then we can see you've got other conversion ratio. You see in here, 1 to 3, 1 to 3, we have using this connection parallel and series. But now then we change to series and parallel, the same transformer. Then again, output is the same voltage. So we lock here, and the input side, I reverse the V out, reduce the voltage by 2, reduce the voltage by 3, and adding together becomes 6/5. So now then this conversion ratio is 6/5. And then for this conversion ratio, when we change the dot rotation, we have a minus in here. That becomes 6. You see the same 2 transformer. By playing around of the winding connection, I have 4 types of the voltage conversion ratio. Not only 4 types, if including original 2 and 3, we're able to have 6 conversion ratio. You see, 2 transformer, we total has 6 conversion ratio by simple manipulation. But in the exam paper, I may ask you, what is the connection when we have SP, PP, PP, PS, SS? Then we may have more conversion ratio. So you can imagine that is so-called power electronic topology. When we play around with the connection method, the topologies, even the dot notation, we are able to manipulate with many conversion ratios, only given you with the two simple transformer. We are able to have, at least in here, you can see that 5, 1, 6/5, and 6, 2, and 3. And then this SP connection, we haven't done SS, PP, we haven't done other. Maybe you can think of many other connections. All right. So that means this is quite interesting. Really simple connection, which we all learned that in the past in the undergraduate. But there's a lot of the implication. That can be a research topic. How you convert all these transformer into different kind of the topologies, different voltage conversion ratio. Do you get my point, right? Then in this lecture, I show you how we bring up a topic, how to work out a new research topic, a new application. By given a two limited resources, we can able to do a lot of the variation. So this we call it topology variation technique. Okay, you get that? The question can extend to 3 transformer. Now, if in the question paper I give you 2 transformer, can you write down all the possible connection to give you all the possible output conversion ratio? Probably you go home, you can think about that. That's a postgraduate level. Undergraduate level, I won't ask them. Yeah. And then now they change the topic. And then for this 1 to 3, 1 to 4, if I 1 to 3 and 1 to 4, what happened? Or 2 to 5, 1 to 2, what happened? There's many questions I can generate. You can then generate a whole picture of a many 2 transformer, give you all of the conversion ratio. And then you can try to build up a formulation, how to formulate this kind of the connection. That can be a research paper, right? That I want to try to say to you, a simple topic you use here, you can generate a research topic. And then there's only 2 transformers. If it now become 3 transformer, there's another journal paper. 4 transformer, N transformer. What's the formulation? Yeah. So that's why don't think about this lecture is simple. I'm sitting here to give you the idea how to stimulate your research, become a new area of the development, new area of the research by using a fixed conversion ratio. So that's a transformer, but that can be a DC to DC power converter, 1 to 3. Then you have 2 DC, build many kind of the new output voltage. And then you got 3 power converter, build another new connection. Or that can be a fuel cell, 1 to 3, 1 to 2 fuel cell. And when you connect them up, then you can have another different voltage. So there's many things we can play around with them to produce something interesting. So that is so-called a topology variation technique. All right, you get that? So think about that. You can help me to write a journal paper on N transformer. What is the voltage conversion ratio? That is one of the interesting ways we can go further, right? You get that? Mm-hmm. So go home to do some study. We can build up a new. I don't think there's many publication on that, but that's really much interesting. Anyway, so topic number 3 will be an auto transformer. So we have been looking at auto transformer. I think that's something we see every day. I think in the lab as well, we only a single winding with a turning knob here. We can adjust the output voltage gradually to adjust other voltage. So that's more look like a tapping transformer, but we only using a single winding. Or you can look more like is inductor, single winding inductor, but using a tapping, we're able to generate voltage in here. Then you can see that an auto transformer is a really special connection of a transformer. The special is that firstly, we don't have any magnetic isolation, harmonic isolation, we have no connection. So that means this side are electrically connected to the secondary side. But many applications, we don't need any magnetic isolation anyway. So if you only like to vary the voltage, you can do the job. And then we also can reduce the winding. We don't need to have two separate winding. We only have one winding. And somehow we can reduce the current. Because you can see that this loop here, we got this current. And this loop here, we got another current. So for the common winding here, the current actually, because the cancellation of primary and secondary side current, this current can be less. So don't think about we got double the current here, but the current here can be less than before because of some cancellation of current. So the copper point of view, we don't less demand for this copper. So that's in a way an auto transformer become quite successful. You can see in many of the simple applications, we tend to use auto transformer. I think in power conversion as well, we are able to use this auto transformer to build up many new topology connection. Okay. So now then, let's see that. For example, like for a step down, say V2 over V1 your N2 over N1, but I've been using N, small n for V1 over N, V2, so I'm just using 1 over N here. So that means in here, so when this term is less than 1, of course, we are calling it step down. So this less than 1, that means the N is greater than 1N anyway. And then next page, we will discuss about the step up will be. So we are using another ratio anyway. So if the voltage conversion ratio is this, the current conversion ratio equal to this, equal to N. Then let's see about the current rating. You see all the transformer current rating for this and that, we got certain current rating. So this current rating, we need to make sure that no current inside the winding will be over this current rating. So it's interesting to see what's the current in here, what current in here, to see what kind of the current when we design the transformer. But bear in mind that the N2 winding here share the total N1 winding. So that's why when we decide this, we may need to be careful to understand what it is. Okay. So next thing to do will be, now we got the conversion ratio in here is this one. So that means the current in here, you got I1 in here, I2 in here. So this current will be equal to I2 minus I1, this current. So obviously this current either less than this one or less than the I1, less current in the common winding. So that means the largest current can be equal to I, because you step down, so this current will be smaller, I1 will be smaller than I2 anyway. So that means the largest current can be equal to I2 minus I1, or may be equal to I2, or may be equal to I1 anyway. So in a case, if this current would be larger than I1, because I1 is falling through in here. We don't care I2 because it's falling outside anyway. This I2 current is not going through any winding. So for this winding, we only I1. For this winding, we only I2 minus I1. So we're checking if when will this winding have high current than the I1, then we come up with when turn ratio N greater than 2. This is only the condition when we have this current higher than I2. The reverse of this one will be less. So this only gives you a correlation how we see the current on two winding, bottom winding and top winding. So the current distribution actually depends on the turn ratio N. So how to use it is more importantly when we do the design, how under which condition and what kind of copper wire we use for any one of them. But anyway, most of case, we just using the same copper for N1 and N2 anyway. So that means this kind of relationship will give us notice make sure that we won't go over the total power rating.
So if n is greater than 2, then there is a chance that I2 minus I1 is greater than I1.
That's right, yeah. So that's why we make sure that under that condition, n will greater than 2. If n is less than 2, then that will be reversed. So that means when n greater than 2, this current is greater than this current. When n is less than 2, this current is greater than this current. That's all. So that means, of course, if your n is vary from 0 to 1, nothing you can do. But if you only have fixed conversion ratio, then you can see how much current here, how much current here. Then you can see which part is the maximum current. You use the maximum current to design your copper to see how thick, what's the diameter for the copper wire you use. So that's the phenomenon. Okay. So another transformer you see will be a step-up auto transformer like this one. Then again, you got I1 current here, then you got I2 current here. So this current will become I1 minus I2. So now then you can see this winding with I2 current. So will this current compared to this current, which one is larger than which one? So again, we can use this relationship. If you want to have I1 minus I2 greater than I2, then since I1 equal to I2 dash, then result will be n will be less than half. So again, you give us the condition when n is less than 0.5, this current is larger than this one, and vice versa. So that's a way help us to do the calculation. All right. Yes.
In previous slide.
Yes.
I1 is the input current, right?
I1 is the input current.
So my question is how can, and I1 is now dividing into two current, I2 and I2 minus I1, right?
That's right, yeah.
So how is it possible that output current is, sum should be like sum of I2 and I2 minus 1 should be equal to I1, right?
That's right, the summation, because it's simple
Yeah.
Kirchhoff law, right?
Why I2 minus I1, even if n is greater than 2, how is it possible that outer current is greater than in?
No, the turn ratio here, the turn ratio 1 over n is our turn ratio. So 2 is 0.5, 0.5 means step down. Because my definition here, I'm using here 1 over n is the conversion ratio, output to input. So bear in mind, that's the definition. That's the definition I've been using for the whole my lectures. Yeah. Other paper may use other definition. So that means n greater than 2, that means it's 0.5, roughly about 0.5, this kind of the range. So we now step down is roughly 0.5. 0.5 is the critical point when we change the current that side, which one is larger than which. So this page only to show you how we design auto transformer or the tapped inductor, right? So which current is larger than which under the tapping ratio, how much it is. So that's very important, especially for you, right? When we design any tapping. So because we see that a simple tapping, we do have a correlation how the current flowing in these two windings are related to the turns ratio. We need this one to design the copper. As an engineer, we need to know what kind of thickness for the copper. And so that is quite important. We can use two separate windings to do that. This is one kind of copper thickness, this is another copper thickness. So this will give us what kind of the relationship between two currents. Of course, in simple tapping transformer, we may use the same tapping. Yeah, it depends on our design. So that's, although this is really simple equality, but give you something for your design, something important. Similarly, I also written down the step-up condition. I put in all this step-up condition, then that means 1 over n will be less than 1, right? Less than 1 because n is less than 1 for step-up, because my definition is like that. So now then we got two current. I1 minus I2 in here, in this winding, N1 winding, and the top winding here is I2 current. So which one is larger? It's quite interesting to see that. So I should say if this current is greater than this current, under what condition? And then I substitute the turn ratio in here, N up will be N must be less than 0.5. That means N less than 0.5, that means will be 2 in here after we reverse it. So that's something quite interesting to see correlation. Okay. Not many textbook, not many material to talk about the auto transformer. Because they usually assume, oh, they're all equal current, equal copper. They seldom mention it. But for more detailed design, tapping, we need to look into that. Because I've been working on tapping, inductor tapping transformer for many years. You can see my journal paper. I got quite a few on this area. There's some topic also quite interesting because usually we can use power converter to control output voltage, but transformer as well. But for simple transformer, like the auto transformer, we can use tapping technique. We can therefore adjust output voltage. The tapping, we can use multiple tapping. In here, only one tapping, but you can use multiple tapping. Then we can adjust output voltage. And then we can, therefore, in here, we need to work out the current rating for each one of them. So that's part of the design. When you publish paper, the editor will ask you how you design this one, what is the current rating, this and that, and then how to design a copper. They did that. So that's why not just the topology, but one session you need to go through the design. So that's some design equation will be needed. Okay. No other paper will discuss that, the real design, but we need to do that. Especially if you find some of your future work, you have to use tapping, have to use a transformer, then there's some kind you need to think about how we make use of the turn ratio. Simple discussion, but the implication will be large. All right. Any question up to this point? So this is a simple example to show what we're trying to deliver to you. Again, we're going to step up tapping transformer. So N1, N2 winding. So I call this N3 winding, easier for us to calculate. So we say N1 and N2 at turns ratio 2000 to 200, as shown in here. Input voltage is 2000. And the output current rating, output current is 500 amp in here. So now then we're asking what will be the output voltage? What is the current rating and kVA rating of the primary and secondary side? We usually refer to the kVA, the apparent power. We don't say W. Because W, I assume phase angle is 0. Although transformer usually phase angle is 0, but however may not be the case. If you connect with the impedance, reactive component, the current may have phase angle. So it's better to use kVA to represent transformer. Same of the discussion for motor as well. We use kVA rather than W. What? So C will be what is the current rating for the shredded winding? M1, that's a shredded winding. What's the current rating? This should be. So that's how we design transformer. Simple question, but there's a lot of the design implication in here. So now then I use the VAB and VBC and VAB and VBC. So that means it's equal to not M3, that should be M3 in here, right? That typo error here, that's M3. So that will be 200 over 2000. So that means VAB voltage equal to 200. So this is, and this is 3 in here. So that's a 3. So 200. So now the output voltage, of course, summation of this and that one. So 200 plus 2000 become 2200, right? And the output kVA rating will be 2200 multiplied by the current 500 here, then become 1.1 MVA. So that's a apparent power rating for the output side. Then for the current relationship, output, that's the basic equation. then we know that this transformer, the turns ratio, output over the input will be equal to the M1 over the total winding, become M1 plus M3. So that means we therefore get the input current will be 550 amp. So slightly different. It's 500, this will become 550 because turn ratio only about 1.1. So the practical rating of the input side, the rating will be 2000 multiplied by 550 become still 1.1 MVA. So the rating, theoretical rating in the primary side, secondary side should be equal anyway with the same transformer. So that's bear in mind about that. All the transformer, the kVA input output with 100% efficiency will be like that. Of course, in practical transformer may not be 100%, then we need to increase the input rating slightly by the efficiency ratio. So the current rating in the M1 winding in here, again, the equation we know that will be input minus the output here from the previous slide. Then that means this only about 50 amp flowing in this winding. Yeah, we get that equation previously. And the rating in N2 winding will be 500. So that means we can see that we have 500 here. So in here, we only have 50. So that means happen to be because of some current cancellation. So this winding have less current rather than high current. Before some student comment, oh, this N2 winding are sharing between the two input output, right? It might be high current, but that may not be the case. Less current because of some cancellation. So that's in a way, auto transformer do have some phenomenon happen to reduce some of the current, some of the rating. So in theory, you can use much thinner copper in here to reduce further your costs. But of course, we are lazy to do that because we don't want to have a new winding here. But if you put the two winding here, put a tapping here, then you can use thicker winding and thinner winding here. But however, if you use auto transformer with a very variable load, probably you only use one piece of the copper all along here. So that's the way we work with winding transformer. Okay, any question up to this point? I think you all learned auto transform in the past, but probably you only learned it in how to change the voltage. But in here, I give you ideas to say, what's the current rating in the transformer? Would there be any saving in the copper? How we do determine which winding have current rating? And the balancing of the power, the input kVA, output kVA, apparent power are equal. So a simple transformer we learned here, but when we visit it from the undergraduate, you can see that we got something new come out in here. The implication will be the tapping inductor. I think I introduced a tapping inductor to see how ask him to further work. So there's another correlation between these two. You may think about in tapping inductor, how we work with the rating, how we work with the saving the copper, how we're working with the cancellation of the current. So that's also another new area we can work with.
So here what we got, like if the turn, if there is a large number of turns, so the rated current should be lower due to cancellation, right?
The turn ratio here.
Yeah, because number of turns in N1 is much larger than N2, right? N3.
N3, yeah.
So current cancellation in N1 is much higher than N3.
Yeah.
Correct?
That's right. So we can actually reduce a lot of copper.
Yeah, because the turn is so less, so there are less cancellation.
You see M1 in here, we got how many turns? About
2000.
Yeah. And then these are 2020.
200.
Most of current appear in here. We got much less current appear in here. So phase says we have a good saving using auto transformer. Save a lot of copper. We have really little current in here. But if you're using two separate transformer, then we need to use a heavy winding in the high current side. So that's the phenomenon we can observe. A simple Kirchhoff's law. You can see that some current are being cancelled. You can save a lot of the copper. Just one of the implications for auto transformer. Simple concept, but it's something we may ignore in the past when we design a tapping system. All right. So that's for today. Then we continue other 2 days, right?